Hi, my name is Imran Yusuf. I am the director of the hardware ecosystem at Arm, and I am joined by my colleague Ashutosh Varma, who is a distinguished architect at Synopsys. The topic of our presentation is system-level verification of PCIe subsystems for SoCs, for SoCs, based on Arm's SBSA, which is the server-based system architecture specification. And we're pleased to discuss the details of the collaboration between Synopsys and Arm in this session with you. The agenda for our talk, I'll kick things off and talk about the Arm System Ready program and the BSA pre-silicon collaboration with Synopsys. And then I'm going to hand it off to my colleague Ashutosh from Synopsys to talk about the technical details of this collaboration, and then we'll summarize the discussion and then end the presentation with a call to action. Arm System Ready value-added differentiation. So I'd like to spend a couple of minutes on this slide to talk about the System Ready program, why it's relevant, why we're rolling it out. And just to take a step back, what I would like to do is talk about the precursor of this program, which was the Arm Server Ready program that we launched a couple of years ago at the Arm TechCon. And the goal of Server Ready was for enterprise class operating systems and the workloads that run on those OSs to seamlessly work on ARM-based servers. And over the last couple of years, that program has seen tremendous amount of success with, and then this has been echoed by our silicon partners, by our OSV partners, as well as our ISV partners. And System Ready essentially is an expansion of the Server Ready program to cover non-data center server segments, such as embedded servers, IoT gateways, automotive. So it's a TAM expansion opportunity for our partners. And the vision is for software to just run on those ARM-based devices for all A-class systems. So if we take a look at the diagram that we have on the left, essentially shows how things are being done today, where there's a hardware platform from a semiconductor partner, and it has their firmware and then the operating system and then the entire stack. So essentially these are silos. And this creates a problem and challenges for our OSVs and our ISVs who are looking to run applications and solutions on these platforms. They tend to be very specific, and you tend to get siloed. With System Ready, the intent is to break down those walls and open up the opportunity so that the software is portable and interoperable. And this obviously provides a great advantage for our software partners to maximize the return on their investment. So the operating systems that run on these devices, then have to be compliant to minimum set of hardware requirements as well as firmware requirements based on the specifications that we have put out. And the OSs should just then boot, and the applications then just seamlessly run on those OSs. And what's really tying this together and bringing it full circle is the pre-silicon validation. So a lot of errors and challenges that we see today are happening post SoC tape out, such as PCIe implementation and the non-compliance. The issues that it creates with the ecosystem, with the operating systems, with the Linux distros, as an example. So the work with our partner Synopsys in terms of having validation and verification IP that tests for this compliance and being able to run OSs before the silicon is taped out allows for higher confidence in the design being taped out, minimizes the design spins, for example. So that's the value that we believe that this collaboration and this program brings for our ecosystem. So it allows software to be portable, interoperable. It's a TAM expansion opportunity. And then it's also a time to market advantage for our partners. So let me talk about the collaboration. So ARM will be offering a pre-silicon BSA compliance certification as part of System Ready for SoC designs that pass the compliance test in pre-silicon. And in terms of what is at stake today for the industry in general, the majority of the silicon today that we have is not compliant to the base system architecture specification that's been out. And while each ARM device is unique, and we celebrate that uniqueness and differentiation, we also would like to open up the market for these products to go into different segments, as I mentioned in the prior slide. And today, we don't have a pre-silicon compliance validation process that ensures and provides confidence that OSs will just work out of the box prior to tape out. So there is that risk that IP blocks will be non-conformant and will require another spin. So the intention of the effort here is to do the following, right? Reduce the risk of SoC developers by catching BSA compliance before tape out. So if we can get rid of the bugs before the tape out, then clearly we're minimizing design spins and further issues downstream with the software, because the software at the end of the day needs to run on the SoC, and we want to get the OSs to just boot and function without any custom patches. And by doing these and taking these necessary steps, we believe that this is going to improve the attractiveness of the product. It'll make the SoC design more robust, and it just also allows the addressable market to expand for the product, as it can go into many different segments, because the number of operating systems that will run on this, based on the program that we've developed, will grow. And I'll explain what that means in one of my subsequent slides. So these are the underpinnings of our System Ready program are a couple of specifications. One is the hardware specification, the BSA, which is the base system architecture, documents the minimal hardware requirements that you need to comply to, and then its counterpart is the firmware spec that you also need to comply to. And then these requirements are distilled in what we call the architecture compliance suite that is available through GitHub. So anybody can download that tool and then run the compliance test to see where their systems are and what if any gaps they have, and then ARM will work with these partners to help get them certified. And these are the, as I mentioned, we're going beyond data centers to include embedded servers, IoT, and we also have requests from large hyperscale customers by being able to just boot Linux out of the box. So these are the details for each of the different bands that we have. As you can see, Server Ready is 2.0. We launched it a couple of years ago, so it's going to be at in terms of level of maturities, it's at level 2. The other 3 bands we're releasing are 1.0, so they're brand new in terms of their availability to our partners. And then what's really also important and exciting for us is the pre-silicon certifications. So we mentioned opt-in. So System Ready program in general, it's not something that we mandate per se. It's an optional program for partners, but there's been tremendous support, and then the value prop has resonated with our ecosystem. So we believe this is just going to help the market and the industry move much faster in terms of deployments and in getting to market. So the pre-silicon certification is an option that we have available today for silicon partners new to ARM System Ready. This is the first step, really, that you would need to take to be system ready and make the task much simpler. And as I mentioned, a lot of the silicon today, the SoCs are non-compliant PCIe, ECAM support are issues, and we believe the collaboration with Synopsys is going to help us drive this paradigm shift to test for compliance before tape out. And now I'm going to hand it over to my colleague Ashutosh from Synopsys to talk about the details of the solution.
Thank you, Imran, for introducing the System Ready program and also the importance of pre-silicon verification around the System Ready program. I'll be going into a little bit more details here about the solution that Arm and Synopsys are building together. So as we know, the system on chip SoC complexity has been growing quite a lot. Now we have IPs coming from various sources, as shown in the picture here. We have a lot of IP from ARM, including the CPU cores, the interrupt controllers, the network on chips, system MMU. We have the silicon partners' own IPs, as well as third-party IPs such as PCIe subsystem root controllers. Now, the requirement for the SoC to serve different markets has grown rapidly. You need to be running different operating systems, such as Windows, Linux, different distributions of Windows, Linux. There are different device drivers that are available for each of these. In addition to these, now we have virtualization concepts. So you have hypervisors and virtual machines that need to run on the operating systems. And all of these operating system distributions, hypervisors, they impose certain requirements on the system architecture for performance as well as for security reasons. One of the things, the challenges that the SoC designers find is that they need to be able to run standard OS and device drivers out of the box. It's very hard to maintain these days specific branch of operating systems or drivers just for your SoC. You need to be able to work on the main line without having to have a headache and a challenge of keeping a separate branch for your SoCs. So this is one of the focuses of the System Ready program, is to ensure that once you have gone through the System Ready certification and the particularly in the pre-silicon world, you are ready for running different OSs as well as drivers and applications. On the system integration side, this makes sure that the system components, which as we show here, coming from different sources, are interconnected well together and are performing well. And particularly, the focus of this solution is on PCIe, which is a boot critical system. As soon as the system comes up, it boots out of SATA drives, SSD drives, GPUs are required, network interface controllers are required, and all of these require that your system must be ready to work with several of these products out there in the market. Doing this at a post-silicon level is a great risk. Therefore, the BSA compliance suite should be run in the pre-silicon stage, and with the benefit of running with the BSA compliance suite is that you don't actually need to run several flavors of operating systems or boot codes. Because those are very heavy in terms of the requirement from running several billion cycles out of the system, out of the design. You need to be able to run the verification program in a very compact manner, in a very targeted manner, and that is what the BSA compliance suite and the pre-silicon solution is targeting, to be able to run these compliance suites and pre-silicon stage, and not having to run full operating systems to validate the environment. So being able to do this in pre-silicon brings, of course, the time to market advantage. You are avoiding respins of the silicon, as well as the debugging of the system level issues is much faster because you're dealing with the pre-silicon environment and you have full visibility into the design. you can achieve hardware-software co-verification closure much faster. However, the requirement for running these compliance tests actually imposes certain requirements out of the verification IP that needs to be used for the solution. For example, majority of the rules that are run as part of the compliance test, they require injection of specific sequences into the PCI endpoint, for example, and they need to check for responses from the PCI endpoint for specific events happening at this, on the PCI protocol layer. So in order to do this, you need a specially designed verification IP, which is targeted for BSA compliance verification. Through this collaboration between ARM and Synopsys, we are providing the complete solution for BSA compliance. As you can see here in the picture, we are providing a PCIe endpoint model, which is specifically targeted for SBSA verification. Your system picture shows here how this ARM components and other IPs come together. The boot code of the system will be developed by the silicon partner, but Synopsys will be providing the PAL or the platform abstraction layer, which allows the ARM compliance suite tests to run transparently on the SoC. And the PAL layer ensures that the compliance suite tests talk to the verification IP that is provided by Synopsys to achieve maximum coverage of the compliance suite and to reach specific corner cases the tests are designed for. So all of this actually ensures that the compliance suite can run through the several levels of compliance, and it gives you confidence that your PCI subsystem and the SoC works out of the box with different operating systems and different endpoints. This shift left is possible because you will be able to run all of this in simulation and emulation. Synopsys will be providing the support for compliance suite integration, the whole bring up of the SoC on simulation and emulation platforms, and also performance validation. The users will be able to run performance scenarios, particularly targeting the PCI subsystem. As I mentioned here, the VIP that we are building will be compatible with both simulation and emulation. And emulation is important because some of the compliance tests, they require several billions of cycles to be run. And this is possible to be accelerated using emulation systems such as Synopsys ZBoost Server. A closer look down on the PCI endpoint VIP. As I mentioned, this is specially designed for BSA compliance. So as you can see in the picture on the right, it provides a user with a modeling option to define a topology, which is very important. So we support bridges, we support NVMe device models, and we support PCI endpoint devices, simple models. Besides the PCI channel that you see here, connected to the design, which is used for the normal PCI protocol verification, the VIP also has a sideband channel, as shown in the picture, which allows us to control and observe the verification IP status through a separate channel without interfering with the normal PCIe channel communication. So this is specially designed again for BSA compliance and allows us to run certain scenarios on the verification IP without interfering or intruding into the regular PCIe channel protocol. Now we'll look into one of the sample example tests that can be run on such a system which require a endpoint to be controlled. This is a level 3 compliance test, and it is targeted towards ensuring that the MSI interrupt facility is handled properly by the system. So the test starts with a normal setup and initialization. Certain information tables are read from the base system that give you us information about the PCI subsystem and the CPU subsystem. And here, as we show, the test will actually give control to the PCI endpoint to be able to generate a MSI interrupt in this, for example, in this case, because that is the target of this particular test. So it instructs the endpoint to generate a MSI interrupt within a certain period. This kind of library for the compliance tests can be actually used to build up more complex scenarios also. That was a brief overview of the verification IP that we are building specifically for the compliance suite. The next area I want to go into is the performance verification of the PCI subsystem, because that is also a very important part of the pre-silicon design verification. So as we know, the PCI subsystem in particular has to handle a variety of applications, ranging from networking, storage, GPU accelerators, network accelerators, and all of them have very different workload profiles, and they interact with the system components in a different way. So it is important for us to understand whether your system will work with different performance workloads, and if there are any bottlenecks. So, for example, you might be upgrading your system to different generations of the PCI protocol from Gen 4 to Gen 5, Gen 5 to Gen 6. You're making a lot of investment there, but is your system ready to really take benefit of the additional bandwidth that is introduced in the system? This is very important to know, because you may move from Gen 5 to Gen 6, but there may be a bottleneck in your system, which prevents you from taking full advantage of moving to this upper protocol. So in order to again reduce the time to market and the respin risk, you want to be able to validate the performance of the system, particularly the PCI subsystem in a pre-silicon environment. Some of the matrices that we collect as part of the performance analysis in terms of TLP payloads, which translate into for the user in throughputs, data block transfers, which may correspond to, for example, packets per second, or IO operations per second, or tasks per second, the latency of the system, how fast does it respond to the events. This is very critical in determining for example, the packet transmission latency or IO latency, depending on the endpoint, and also the throughput of the interrupt, because the system needs to respond to the IO events happening in the endpoints. So all these key matrices need to be covered and measured and simulated for different workloads. Here's an example of one of the workloads that you want to be able to simulate, and this is very common in NIC devices with network interface controllers, storage devices, as well as GPUs. So what is shown here is a general picture of the stack of the system with the application kernel, your SoC, and also the main memory of the SoC, which is used as the mode of communication between the application code, the drivers, and the endpoint devices. So essentially, the drivers and applications, they set up the PCI device to work out of memory structures such as ring buffers, and commands and data are placed in ring buffers. The devices then go through DMA to access the data buffers and to receive their commands and put the data back into the data buffers. So all of the activity from the device point of view, which carries this data, is through DMA. And there may be some other interaction going on directly with the device through the memory mapped IO operation, but bulk of the data is transferred through DMA. There may be other system level interaction up into the operating system in form of interrupts. Interrupts need to be serviced. And there might be some polling going on from the driver side. So all this together results in a scenario in which several system level components come into the picture. You will have interconnects, you will have system cache, you will have DRAM controllers, of course the PCI channel. All these need to work together, and you need to be able to ensure that the particular PCI trafficking pattern that is for this particular workload is being handled properly through the system, through the DMA and reads and writes. Now we'll talk about how this verification IP is integrated with the rest of your environment. Here's a picture of a typical verification environment. You see in the block diagram in a typical SoC and some verification IP components. At the top, you can see an instantiation of the Synopsys PCIe verification IPs, especially targeted for system-ready certification. This picture was explained earlier. It allows you to model different kinds of PCI topologies. There's performance monitoring built in here. There's a sideband interface to control and observe the verification IP itself from the tests. Some of the other components in your system can be the memory here, which is used for, as we said, for setting up the performance tests, data buffers. For example, there is a messaging tube, which will be, for example, can be a user terminal through which the compliance tests can be run and the results obtained and the performance data obtained. And all of this actually environment is common whether you want to be running the certification tests or you want to be running performance tests. So the common environment should be able to serve both purposes. Running the tests in Baremetal involves first getting the test suite software. These are now being provided by Synopsys, and we also provide what I showed earlier as the platform abstraction layer. Together these two are provided to the silicon partner, and the silicon partner then takes up and integrates this software layer along with their boot code. Along with this, on the design side, the VIP is integrated into the test bench, and then the compiled test suite boot code is run on the SoC to generate an SBSA report. This is the certification flow here. You will select a certain level of compliance. You will run the tests related with that compliance level. If all the tests pass, then you can move forward and send the report to ARM for their approval and certification. They might be, if the tests fail, then of course this is where the pre-silicon stage will allow you to actually debug and understand what issues exist in your design in terms of the compliance. If required, you can discuss waivers for your specific design situations if some of the compliance suite tests are not relevant for you. And here is the delivery overview of the overall solution. As you can see, the various parts of the solution come from different sources. In particular here, top left corner is providing the SBSA test specifications in the open source public domain, along with a API definition that we need to adhere to from Synopsys side in order for us to be able to exercise the VIP working together with the compliance tests. So the top green box here are all of the components of the solution provided by Synopsys, including the platform abstraction layer, the verification IP, the performance measurement of the system, performance tests, which are specified by ARM, are implemented by Synopsys, along with users' flexibility for the user to give different parameters to the tests. These together will come to the design that you are developing. Some of the VIP things will be integrated at the design level. Some of the API and tests will be integrated into a software library. Similarly, the performance tests will also become part of the software library. And by running these software and hardware embedded tests together, you will be able to generate a report out of the system, which will be shared with ARM for certification. Specifically, silicon partner responsibilities here to make sure you understand what will be your role in the overall bring up and certification with these compliance tests. Of course, since the design is specific to your hardware IPs, the boot code will be a responsibility of the silicon partner. For this, there are some guidelines available from ARM that can be used to develop the boot code that will be compatible with running the tests, because the boot code needs to provide certain system level information to the tests. The software integration of various pieces, as I mentioned, the compliance suite, the platform abstraction layer from Synopsys, the performance test suite from Synopsys. This will, along with your boot code, to create a binary image that will run on a SoC, will be done by the silicon partner. Of course, Synopsys and ARM will work together to achieve this software integration. In terms of a example system, because there are lots of IP involved here, we will not be providing any example system because of IP distribution restrictions, but we will help you build the final environment specific to your IPs and specific to your SoCs. And Synopsys will be providing the support for the VIP integration, of course, and also the setup of the VIP for the compliance suite. The running the BSA and compliance suite and performance analysis will be done by the silicon partners, and the results of these can be shared with ARM. But essentially, you will be able to analyze from the errors and the performance metrics what are the next steps to take in your design in order to mitigate or address those issues. In summary of this session, ARM and Synopsys are collaborating and launching a pre-silicon BSA verification solution. This shifts left the task of compliance and removes a lot of the risk associated with doing this validation at a post-silicon level, and it also improves your time to market. The system-ready pre-silicon certification is an option at the pre-silicon level, and it allows you to catch the risks before tape-out. Reducing the time to market risk and taping out with confidence that the PCI systems will work out of the box with different OS and drivers is really the whole goal of this system-ready program. At this point, I'd like to invite Imran back to close the session and outline the next steps for the silicon partners.
Thank you, Ashutosh. To essentially summarize with a call to action, this is a major paradigm shift for the ARM and its ecosystem. That the pre-silicon is a first step that greatly simplifies the certification towards final tape out. We are actively seeking early access partners to engage with us and start new designs beginning of the Q4 quarter. And Ashutosh and I are looking forward to hearing from you. And thank you for your time and attention.